Hello, Professor. This is Julia Schneider from Survey of Calculus, Math 130, and this is my video explanation in which I'm providing additional examples for the following learning targets: L4, D1, D2, and D5. These three learning objectives are from the first exam, and this learning objective is from the second exam. So I've done this video a whole bunch of times, and I'm just gonna run through these examples super quickly in the sake of time. But the first learning objective says, I can determine the points at which a function is and is not continuous and can use continuity to evaluate limits. We have our graph here. We have our values at which the function is not continuous here, and as well as the explanations. So we have x equals 0. This is an asymptote. This isn't like the same thing as a hole or a jump. It's just because x equals 0, there's an asymptote, and that makes this function not continuous, as you can see. But at x equals 5, it's not continuous because there's a hole in the function, and at x equals -5, it's not continuous because there's a jump in the function. And then we evaluate the limit here as x approaches 0 from the right and from the left. This is supposed to say right and the left, and this equals -infinity, and this equals infinity, and these are not the same value, so we know that it's not continuous there. The next example says that f of x equals x plus 3 over x plus 3 times x minus 4. And we know that there is an asymptote at x equals 4. And then we take the limit of f of x as x is approaching 4 from the left and the right. And this is -infinity, this is positive. They do not equal each other. So we know that there is the asymptote here. And then we know that at x equals -3, the function is not continuous, and there's a hole in the function. And so yeah. And then for D1, which is the second learning objective I'm talking about, it states I can accurately conceptualize the derivative beyond describing how to calculate it. So here we have a cylindrical tank of oil is leaking. If V of t equals pi r squared times h and r equals 6 feet, what does v prime of t mean in general? It should say v prime, this means that basically the rate of change of the volume with respect to time, and then b at 1 hour, the tank is losing volume at a rate of -36 pi dH/dt, so with respect to time. So this means that the tank is losing oil at a rate of -36 pi times the rate of change of the height of the oil in the cylindrical tank. So yeah, we basically use 1 hour to demonstrate the rate of change with respect to time. And yeah, on to the next example. The population of ticks in the forest is represented by P of t equals 1,000 over 1 plus 3e to the -1/2 t, or 0.5 t, where t equals days from June 1st, and then p is the measure of the number of ticks. And then this says, what does p prime of t mean? At day t from June 1st, prime of t is the rate of change of the population of ticks in the forest. And then b, what does p prime of 28 equals 12 mean? Hold on. And then on June 28th, the tick population is increasing at a rate of 12 more ticks in the forest per day. And so yeah, on to the next learning objective, D2. I can explain the parts of the limit definition of the derivative. I only did one more explanation for this, and it is the other formula. So let's explain this. The limit as x approaches a, f times x plus a minus f of a, times a, and then over x minus a. And this is basically showing you like change in y over change in x, which is basically, the slope part of the definition. So let's get into it. A says, what is the limit part of the definition? The limit part of the definition has x approaching a because our change in the slope part of the definition, as the value of x approaches the value of a, our change in x becomes closer and closer to 0, or an infinitesimal, which is a really small number. So we're trying to have it be as like close to 0 as possible, kind of. And then B says, what is the rational part of the definition / like what does it mean? And the rational part of the definition is the fraction, or the change in y divided by the change in x. The denominator is the change in x approaching 0. So we can derive an instantaneous rate of change. And then the numerator is the change in y between f of x and f of x plus a, which is like next to f of x, or the instantaneous change in y once x essentially equals a. And so that is fully explained, kind of super simple. And then the last one, which is just computing derivatives using multiple rules in sequence, which we have more examples of here. And yeah, I'm gonna go like 20 seconds over just to give a little insight, but basically I use the product, power, and chain rule here, and the quotient change and log derivative rule here. I mean, this is not like an actual official rule, but I just wrote it down to demonstrate what I was doing. And yeah, thank you so much for watching these videos, and have a great rest of your week.